Can everybody still hear me? Just a quick yes. Just one confirmation from somebody.
Yeah.
So we start with the conservation of mass, okay? So we have del rho, del t plus del rho ui del xi. Mr. Kosra, hi. It would be nice if you remove your stuff again.
Would you please delete this?
Thank you.
Thank you.
That's good. Okay. I have turned you off again. Mr. Kosra, hi. Can you still scratch and scribble? No, you can't. Good. So this is naught, okay? So we assume that the density is constant. To simplify things, we end up with the equation del ui del xi equals naught. Now in the next step, we do the Reynolds decomposition. For reminder, ui equals ui bar plus ui prime. This inserted gives us del ui bar del xi plus ui prime equals, we can write this in a different way, del ui bar del xi plus del prime del xi equals naught. So the first step was decompose. Now the next step is to average the equation, because we are only interested in average quantities. So if we average again, we end up with del ui bar del xi bar plus del ui prime del xi bar equals naught. So the next step that we did was we average again. You might call it re-average. But to be honest, it's the first time the whole equation is averaged. And now we have to look a little bit at the mathematical properties of averaging. And it turns out that averaging has commutate with spatial derivatives. So we can swap the order of spatial derivative and averaging. So then we end up with del ui bar bar del xi plus del, excuse me, I made a bad mistake a line up. I have to remove this again. I'll show you where the mistake is. It is here, right? We had a ui prime, not a ui bar. So we have a ui prime del xi, and that term is averaged equals naught. And now we average. Or we have just averaged, and now we reformulate that. And with the spatial derivative and the time averaging being commutative, so we can swap the order, we can just write del ui average over del xi plus del ui prime average over del xi equals naught. Now we have ui prime prime equals ui prime. Ui bar bar equals ui bar. In other words, if we average an average quantity, we get the original average. If you think about numbers, it's fairly easy. If you think that the average height of a person attending this class is 1.78 meters, and then you want to calculate the average, it's again 178. Because if you look at the average gives you one number. So in other words, you have one sample only. And if you have average over one sample, you got the original value. Okay? So ui bar bar equals ui bar. Ui prime bar equals naught, right? Because ui bar prime is the deviation from the mean value, and the mean deviation from the mean is naught. And we end up with this equation. And this is a very big equation for us. It's a very important equation. It's the conservation of mass equation in mean quantities. So here, what we have written down now is an equation that just looks like the previous continuity equation. All that has changed is that here we do not write ui anymore, but we use ui bar. In other words, when you have a computer program that is programmed to solve the momentum equation, we can use the mass equation. We can use the same original computer program without any change to solve the mass equation. This is nice news. Only this time we have to interpret the velocity in a different way. We now interpret it as a mean velocity rather than an instantaneous, highly fluctuating velocity. Okay? So this was our conservation of mass. Step 1. Questions? A moment. For some reason I don't see the chat right now, but I'll get to it. Okay. No questions. Okay. Now let's look at the conservation of momentum. Things are getting a bit more exciting now. First, I have to write down the conservation equation. Remind me if I make any error. Del rho ui del t plus del rho ui uj nach del xj equals minus del p over del xi equals nonsense, plus del x j viscosity times d ui dxj plus del uj del xi minus two-thirds del ij del uk del xk plus rho gi, where rho gi is the gravitational term. Please tell me if I made a typo anywhere, but I think the equation should be correct. If anybody sees a typo, tell me, okay? So, now in the next step, we do the Reynolds decomposition. So reminder, Reynolds decomposition is the step where we say ui equals ui bar plus ui prime, and p equals p bar plus p prime. Okay? We again assume that we have a constant density. If the density is constant, then we can take the density out of the differentials, and we can also look at terms that will become zero. If the density is constant, this divergence term here will be zero. if the density is constant, we also end up with this term here in combination with that guy becoming 0. Because you can write, obviously, this guy here, this has first this derivative, right? So this is del xj mu del xi uj, and you can swap the order of the differentials. So you would end up with mu del xi del uj del xj, right? And this here, again, is 0 for a constant density, because this is the divergence of the velocity field, and the divergence of the velocity field for a flow of constant density must be 0. This is the conservation equation for mass, okay, or the continuity equation. So I remove that again. And I write the simplified equation. We have del ui del t plus del ui uj del xj minus 1 over the density del p del xi plus del, we now also assume constant viscosity, so we can take the mu out, del xj del ui del xj, or we can just write this as del square ui del xj squared plus the gravitational term rho gi. Okay? Now we have to look at all these terms here, which I will do now in the next step. So we have the accumulation, we have the convection, we have the pressure gradient term, we have the viscous stresses, and we have gravity. Questions so far? Good. Let's start with the accumulation term. The accumulation term is del rho ui del t. If we take this term and we decompose it, we end up, after step 1, decomposition, with the term was already del ui del t. If we take this and decompose it, we end up with del ui del t. We have ui bar plus del ui prime del t. Okay, this is our decomposition. And now in the next step, we average it. We end up with del ui bar bar del t plus del ui prime bar del t. And this is del ui bar del t plus, here we have the mean value of the fluctuation, which is always 0, so essentially plus nothing. This is the remaining accumulation term. Now you might say that this term here is actually 0 because of the fact that ui bar is a mean value, so this is constant, and we have a time derivative of a constant quantity. So in other words, this term becomes 0. But now this is interesting. If we write a flow solver, a CFD computer program to solve the flow field, this term will only be 0 once we have achieved a converged solution. Up to the point of achieving a converged solution, we may need this term to actually drive our solver, to actually make things converge, if we build an iterative procedure. So for this reason, we do keep this term, knowing that it's artificial and that for the fully converged solution of our equations, this term will become 0. Okay? So what I write is just this term goes to 0 with the convergence of our computer program. Okay? Any questions? Yes, no? Here again, it's nice if somebody just types no so that I know that I'm still connected. Thank you. Good. So this was the first term. Then let's have a look at the gravity term. The gravity term is just effectively, BI. It's just the gravitational acceleration. If we decompose this, it doesn't change actually because G was a constant already, so it stays Gi. Everything fine. Let's look at pressure. Del P, del Xi. In the first step, we decompose it. We get del P bar, del Xi, plus del P prime, del Xi. We average it. We end up with del P bar bar, del Xi, plus del P prime bar, del Xi. And this again, as here the mean value of a fluctuating quantity, so this is 0. And here we have the mean of a mean, so essentially the mean value of only one single sample, which is the identical value of the sample. And we end up with del P bar del Xi. So the convection, the pressure gradient term looks like our previous pressure gradient term. It's a beautiful term. It looks all nice, all simple. It has not changed. Here, like with the gravitational term or the time derivative term, we can just use our existing flow solver as before. We do not have to modify the program. We can just use the same program. We just have to interpret the quantities differently. What we treated as an instantaneous velocity in the past is now treated as a mean velocity. Beautiful. Questions so far? Again, please, one person writes no if there are no questions. Good. Now we have the viscous term. The viscous term was eta del ui del squared ui del x. I x, hold on, del x j. Right, I think that was the viscous term. Is that correct? No, I think it was uj xi xj. Okay? Please correct me if I'm wrong. So here again, we do step 1, which is decomposition. We get mu del squared, second derivative. Yeah, hold on, there's something. check. I think that xi squared would not make sense. I may have been sloppy there. Just a little moment. Yes. Yeah, okay. Hold on. xj del xj. Okay. So this is the correct one. Thank you. So step 1. Decompose mu del squared ui bar del xj plus del squared ui prime del xj del xj. Okay. Step 2 is average. So we end up with mu del squared ui bar del xj prime plus del squared ui prime bar del xj del xj. Okay. So this is fairly nice because here again I have this double average, which is the same as single average. And here again we have the mean of a fluctuating quantity. So we can simplify the whole thing and get mu del squared of u bar del xj del xj. And that's it. So even our viscous term looks a lot nicer now. It looks just as nice as it used to be originally. So if the density is constant, we can write the viscous term, the viscous stress term, like we did before. Nothing changes in its style, in its presentation. It stays the same term. Only interpretation changes because now we interpret it as a term of the mean velocity of the time averaged velocities instead of as a term of instantaneous velocities. So it's easy. Now looks as if we could write the momentum equation just in the same way after time averaging as we did before. That this is not true, I will show you with the final remaining term. But first, any questions? Yes, okay, let me see. No, all right. Mr. Absi, you have a question? dxj instead dxj. Yeah, I know you're referring to this here, right? Oops. Yeah, obviously in the derivatives there should not be a prime there. This was, to be honest, it's not so easy to write electronically. It's not as easy as otherwise, and then you sometimes end up writing things a bit messy. And I think I made this look like a prime, yeah? So apologies. Here, there's no prime, okay? And also here, there's no prime. Thanks, Mr. Absi. Right, now let's look to the remaining term. The remaining term being our convection term. So, del ui uj del xj. What's going to happen with this guy? First, decompose. Del ui bar plus ui prime times uj bar plus uj prime del xj. Okay? So this can be written as del xj of ui bar uj bar plus ui bar uj prime plus uj bar ui prime plus ui prime uj prime. Done. Okay? Now we have to average it again. So we end up with del xj times. And again, we use the property that the spatial gradient and the time averaging do commute because they are operators in different dimension. Spatial averaging is in 1, 2, 3 dimensions. Time averaging is in the 4th dimension only. So we have ui bar uj bar bar plus ui bar uj prime bar plus uj bar ui prime bar plus ui prime uj prime bar. Okay, now we have to see if we can simplify this. We get del xj. This here is one constant value in time. This is one constant value in time. So the product is a constant value in time. So only one sample. And if we average this again, by using this second averaging bar here, we still get the same value. So nothing has changed. So it stays ui bar uj bar. This term here is interesting. What you see here is a constant times fluctuating quantity and then the average. Now bear in mind that the averaging procedure is actually defined by an integral. So something like an integral over ui bar uj prime in time would be the mean value that we have here, okay? If this is an integral, we can take the constant ui bar out of the integral. In other words, meaning that this expression can be written as ui bar u bar or bar, it doesn't matter, yeah, because it's constant, times uj prime bar. Uj prime bar here, this is 0. The mean value of the fluctuating quantity is 0. So this guy here becomes naught. Now for symmetry reasons, this guy must also be naught, right? It's the same thing. We can here again write this as uj bar times ui prime bar. And this ui prime bar here would be 0. So this is nice. We lose a lot of ugly, nasty terms. Then the only term that stays is ui prime uj prime. Now, here, this mean value. How would this mean value be calculated? It would be calculated by integral ui prime uj prime dt from t naught to t naught plus t 1 over t in the limits of t approaching infinity. Yeah? This is how we evaluate this, the mean value of this guy. Up here, I have used the fact that I could just take the constant ui or uj here out of the integral, then then things were easy. But here, ui is not constant and uj is not constant. They are both fluctuations. I cannot take any out of the integral. In other words, we have to keep this term. So we have to write plus ui prime uj prime bar. This here is the Reynolds stress. This is an unclosed term. It results from the fact that when we wrote down and derived these equations, we threw information away. We threw the temporal information away. And this means that there's not enough information to really close the equation left. And this shows here, because here we don't get rid of this guy. Is there an easy way to think why this would not be 0? Well, let's just look at u1 prime, u1 prime, okay? So this is just the fluctuation of the first velocity. And this can obviously be written as u1 prime squared bar. And since we have a square of a quantity here, this square of the fluctuation can never be negative, it's always positive. The mean value of a number that's always positive or 0 is always greater than 0, naught, okay? So we cannot get rid of this term. It gets even more interesting if we have ui's and uj's in different directions. So we might have u1 prime times u2 prime. So the velocity in the x component times the velocity in the y component. Because if these are correlated, we end up with stresses. Okay? So, what we end up with, del xj ui bar uj bar plus del xj ui prime uj prime bar. Okay? So this guy here is the term that is already in our computer program, in our CFD program. Just this time we interpret the velocity as a mean velocity, ui bar and uj bar, instead of instantaneous velocity, ui and uj. We can use the same CFD program, it's really cool, but we have to add this new term. And now I'm choosing the most ugly colors that I can find on my computer, because it's a very ugly term. It's not closed. We do not know how to calculate it. We have to get the information about it from some other ways. And this will be turbulence modeling. We speculate what affects this term, what creates this term, and then we will use some clever ideas, some guesswork, some qualified guesswork to actually estimate ui prime uj prime bar. So this is the main task of turbulence modeling, of getting this term here. Questions? No questions. I mean, if you look at this, it's quite puzzling actually. You know, everything looks so nice. All the terms just behave in a nice way, only this term does not. The reason being that this is a non-linear term. We have this product, and if you average over this product, it doesn't go away. In a philosophical way, what we have done is we have taken the Navier-Stokes equation that apply for the full physics, everything depending on time, with fluctuations inside. We say we do not want to know the information, so essentially we take the equations and throw one entire dimension away. The whole simulation of time is kicked out because we replace everything with temporarily averaged quantities. Now it's clear that the information of time that we have lost must show somewhere. And this here, this is where the lost information of time gives us a term that we cannot know. So in other words, you might even think of this term is the effect of time. So time does have a distinct effect here. Time cannot be ignored. Time changes the mean value of the solution. Okay, any more comments or questions? Otherwise, I will remove the slide. Nobody's typing? Good. Now, one very important thing. You may not think about it, you may not have thought about it. A problem we very often see in the oral examination is that people write down this guy, and then they are supposed to simplify it, and we know the correct answer is UI bar, UJ bar. This is not UI, UJ bar. This is very important to understand. Yes, you are allowed to not write this bar, because the product under that bar is a constant value, so essentially you have one single sample. Here, you have written down a correlation of two quantities. If we were to take this thing, we could end up looking at the Reynolds decomposition again. After all, that's how we started, right? We would end up with UI plus UI prime, UJ plus UJ prime equals, and then you would end up in the end with what we've seen before, UI bar, UJ bar plus UI prime, UJ prime bar. Yeah? So obviously, it's very, very important to remember and to not confuse it. Very important that this is not an identity. This expression here equals to that expression, but it does not equal to this expression, okay? So that also means for you that when you are working with these averaging operators, you have to be very careful. Remember, this with a break in here is something very different to a continuous line, okay? Here, we have two mean values that are multiplied. Here, we have a product of two fluctuating quantities that is then averaged. Very different beasts. Okay, so we are through with that part. Any questions? Then I will go back to the original slides. Let me see, does this work? Not like this. Okay. So we have arrived at this equation, which looks like the normal conservation of mass, just now with mean velocities. That equation, which looks like the normal conservation of momentum, but this time with this ugly added additional term, the Reynolds stress tensor. Okay? Good. For now, we'll make a break of 5 minutes. One thing first. The cleaner is cleaning up the room next door. Can you hear me well, or is there significant noise for you? If there's significant noise, I will move to the headset. Please let me know. It's all good, Herr Minhorst? Is it fine for everybody? Okay, good. Then we gather again here in 5 minutes, all right? at 10 past 10. Okay, meine Damen und Herren, Sie sind wieder da. Sie können mich gut hören. Okay. Then let's move on. Next slide. So how can we interpret these Reynolds stresses? They are funny beasts, right? If we look at the Reynolds stresses here, mathematically, they are something fairly similar. They are a stress. They are something fairly similar. These terms and these terms, they both provide us with stresses. So we can actually say that molecular stresses and turbulence stresses have the same effect. They transport momentum in gradient direction. So if you have a fast flow and a slow flow, what the viscous stress does, it takes momentum from the fast flow to the slow flow. If you have a turbulence stress, fast flow and a slow flow, then again momentum is taken from the fast zone to the slow zone. If we look at the viscous stresses, here, the momentum transfer happens by little mass dots bouncing around, flying around, and on average distributing equally in all directions. That means that if you have a fast zone and a slow zone, there's a high probability of some of the fast little mass particles ending up down here in the slow zone, and some of the slow mass particles from down here ending up there in the fast zone. This is due to random molecular motion. These little mass points are molecules, and they will just fly around, and when the fast molecules from the fast zone end up in the slow zone, they carry momentum there. And if the slow particles from the slow zone end up in the fast zone, they carry a deficit of momentum there. In other words, we have a smoothing effect. We have an effect where here the velocities will get smaller, and down here the velocities will increase. This is how viscous forces work. If we move to a turbulent flow, we have the same thing, just this time in green. We have a fast fluid up here, a slow fluid down here. Now we have little turbulent eddies moving the mass particles about. We are not looking at little molecules now on their own, but now we just look at some bigger items, some blobs of fluid. And the turbulence will push some of them by a vortex down there and others up. They will just move randomly in all directions. So again, if there's fast fluid and slow fluid nearby, some of the fast particles will end up in the slow zone, carrying momentum there, accelerating the slow zone. And some of the slow particles from down here will end up in the fast zone, carrying momentum with them, carrying a deficit of momentum with them, providing a deficit to momentum to the fast zone. And the result is up here we get slower, down there we get faster. When we look at the molecular motion, we have something like a molecular velocity. These are very, very high velocities. Molecules are very fast, at standard conditions, a few thousand meters per second in air. These molecules travel for a certain distance. This is called the length of a free path. So the average free path length is the distance a molecule travels before it's hitting and crashing into another molecule. The viscous stress is a result of the velocity of the molecules and the free path. So you can increase the viscous stress if the free path length is bigger, and you can increase the viscous stress if the velocity fluctuations are higher. In a turbulent flow, we have very big items rather than the small molecules. But in the turbulent flow, they travel over the distance or size of a turbulent length scale, so over the distance of an eddy. Whereas in the laminar flow, they only travel over a very short distance, but very fast. So viscous stresses, very high molecular velocity, but only carried over very small distances, mean path lengths. They are typically in the nanometer range. For the turbulent stresses, very low velocity fluctuations, maybe 10% of the mean flow velocity, but therefore a traveling distance in the millimeters, in the range of millimeters. So carrying momentum very fast, explaining that the turbulent stresses can be very, very large in spite of the fact that the velocity fluctuations are very small compared to the velocity fluctuations of the molecules. So this is an analogy between viscous stresses and turbulence stresses that you should always keep in mind. It's very useful, and many ideas for turbulence modeling are based on this idea, on the similarity of viscous stresses and turbulence stresses. But don't take this analogy too far. The molecules here, the molecular motion, they satisfy the continuity equation by statistics. If you look at individual molecules, you don't have to bother much about statistics. In the turbulent case, we end up with very large and very few blobs compared to the molecules. And they also have to satisfy continuity. So in other words, this lump of mass here can only go down there if it displaces the mass there. So this gives us a slightly different behavior. So we cannot just use the simple idea of viscosity to describe the turbulent flow, but we can adapt it a little bit, adjust it, and then get fairly good turbulence models. This is just about interpretation. This slide was meant to help you think about the behavior of turbulence and laminar flows with molecules. Questions or comments, please? Questions, suggestions, amendments? Mr. Karim, I see you typing. Feel free to turn on your microphone. That might be quicker, but you can also continue typing. I'm just waiting for your message. Fluid particles switch phases. Well, if we think of a fluid particle, right, a fluid particle is something that we treat as a continuum, so it will consist of a few million molecules or more. And if we have a fluid particle here, so a few million molecules, so a gas of, let's say, a cubic meter or a cubic micrometer or something, and some other item, fluid volume is coming here, then obviously it has to replace it or switch places, yeah. They do not switch places just like this, right? But if this guy is coming here, then that guy has to go somewhere else, wherever that is. Right, next slide. So our result were these equations. The mean, conservation of mass, mean or conservation of momentum. So these equations are identical to the original Navier-Stokes equation, with the only noteworthy exception of the Reynolds stresses. So we can reuse our CFD codes, which is nice. The flows behave similar to a laminar flow, but we have this additional term, which has strong considerable effects. In a way, you see that here we have an additional stress. This is a stress term, and here's an additional one. So we no longer have our viscous, or our stresses only depend on this guy, on that velocity term here, but also on the fluctuations. So in a sense, we now have a different material law. It means that Reynolds stresses can be treated like a non-Newtonian fluid. So in a sense, a turbulent flow is a non-Newtonian fluid, okay? Now let's think about the sign of the Reynolds stresses. Here we see different profiles for velocity fluctuations. Here's a U prime, and here's a V prime. Here's another U prime that has been scaled down. Here's another V prime, and another V prime. So if we want to look at the U prime, V prime mean, it depends on very much how U prime and V prime behave relative to each other. So let's look at this example here. We have a U prime and a V prime. If the U prime line and the V prime line are perfectly in phase, that means when U prime is positive, then V prime is negative. Or here, where V prime is positive and U prime has become negative, then we always have a negative product. And the mean value of this is a negative quantity. So we get a negative mean stress U prime, V prime bar. We may have different situations though. we may have a situation like here. We have a positive v prime when we have a positive u prime, and a negative v prime when we have a negative u prime. So when the product is always positive, we always have a positive Reynolds stress. So we can already say that depending on how u and v behave relative to each other and fluctuate relative to each other, we will either see positive or negative stresses. Now we can also have different things. We can have a situation like this, where we have u prime and v prime being shifted in phase by 90 degrees. So when u prime is high, then v prime is 0. When v prime is high, then u prime is 0. Or when v prime is 0, then our u prime might be negative. In such cases, we will not end up with any Reynolds stresses, or they will be uncorrelated. Another way for not having Reynolds stresses is if we have very different frequencies. Here, u prime and v prime. They fluctuate at different frequencies. In this case, we will have here, where the v prime is positive and the u prime is positive, a positive contribution. V prime is negative here, but u prime is positive, negative contribution, and so it continues. Negative contribution and positive contribution. We also have no Reynolds stresses if the quantities are just completely uncorrelated. So if the two guys are just completely independent, so the one being a sine curve and the other one just having nothing to do with it, with a very different frequency content. But very often, we actually will find that we have one turbulent fluctuating signal, maybe looking a bit like this, some turbulence and fluctuations superimposed with a sine wave or with a low frequency signal, and another velocity component looking like this. And we look at them, then we find that we will end up with a finite positive or negative Reynolds stress instead of 0. So in other words, the Reynolds stresses will affect the physics of our flow. They are things to count with, they are things to consider. So, how to determine the turbulent stresses? There are two ways. The one way is to derive a transport equation for the turbulent stresses. The other way is to exploit the similarity to the viscous stresses. Well, originally I wanted to do this today. I have to check with Louis if he's doing it in the tutorial, otherwise we do it next week. But the other way, I can already tell you in advance, to exploit the similarity to the viscous stresses, we actually treat the turbulent stresses like a viscous stress, and we just consider that turbulence most of the time statistically behaves like an increased viscosity. So the effect of turbulence is the same effect as the effect of increasing viscosity. But then, if we apply the so-called Boussinesq approach and add a turbulent viscosity, the question remains, how strong has the turbulent viscosity to be? How do we determine or calculate it? So what I want to do today is to derive the transport equation for the Reynolds stresses. I will give you a brief outline of this. You see, it will take a little bit of time. It is not worth squeezing in now. We will do it in the next lecture. We stop at this point. Louis, a question directly to you. Are you deriving the equation in the lecture, in the tutorial today? No, I think not, huh?
No.
Good. So we do it in the next lecture, okay? So in the next lecture, what we are going to do is to derive a transport equation for this guy. With that, I'm at the end of the lecture. I was a bit slower than normally, but I was explaining a bit more. I think it works nicely that way. I think it was good for you to understand these basics. And the next time we'll take the time for the averaged transport equation for the Reynolds stresses. So with that, I would like to at least take some 5 minutes for questions. So please ask your questions. We've covered very important stuff today. It's probably the most important lecture that we do. Questions? comments. This is nice, Mr. Cooper. Thank you.
A question.
Ja, bitte.
A few slides ago, you had the little sketch with the viscous stress and the turbulent stress.
Viscous, yeah.
Viscous, okay. On the right side, the turbulent stress, the particles are slightly larger than on the left.
Yeah, on the left-hand side, what we look at are essentially molecules, single molecules. And on the right-hand side, we just think of a blob. You can think of this as a drop of liquid. Obviously, there's no real distinction of one drop of liquid in a glass of water from another drop, right? But you could just draw lines around it and then look how it is transported and how it's deformed in the process.
Okay, thanks.
Yeah? So the molecule is really countable. It's something discrete. It's identifiable. A drop of fluid only becomes identifiable if you define it as your system. So you artificially draw a line around it, around the molecules inside and outside, and then you just track all these molecules so that you can say it's still my old system. Okay?
Okay, yeah, good. Thanks.
Mr. Apsi? One can understand UI, UJ product as a cross product of two matrices multiplication. Okay, maybe, but I would rather think about the vectors, right? You have two vectors. Okay. More questions? If not, then I'd like to thank you for your attention. I would like to ask Louis to take over. Perhaps Louis wants to make a break, but this is up to you.
Yeah.
Then I talk to you again next week. Thank you, guys.
Thank you, Andreas.
Bye-bye.
Bye. Okay, guys, yes, yeah, just let's take a break, 5 minutes. We'll be back in 5 minutes, yeah? To start the exercises. See you. Okay, guys. Yeah, let's start. I hope that you're doing well. Okay. Actually, this section is focused. I mean, just the second part of the probability density functions equation, and is related to the mean, value, variance, standard deviation, which, yeah, for you is quite easy, assuming that you captured the concept last week, and you have reviewed this, the definition of related to the integral for mean values, variance, and standard deviation. Let's start with this first exercise. Yeah. What we have here is this equation here, and they say that Q is defined as this equation. And U is a random variable, A and B are constants. And we should demonstrate that A, B, C, and D. Could you please just type? Can you hear me properly? Okay, thanks. All right. Yeah, in general, one second. In general, if Q is a function of U, yeah, as you know, the mean of Q, let's say that the mean value of Q as a function of U is given by the following equation. U mean value is just the integral infinity U F U D U. Yeah. We have to replace the value of this. Yeah, just going to. Okay, this is just the mean value, but what we know. Yeah, say if I have a space here. This is our equation for Q. Just replacing value into the above equation, this equation here, we get the following. Get second. Here. Here. And we just have to solve the integral. Let's do this. I'm just going to split the integral. This. Let's say that A and B are constant, so okay. But remember that this part here, just this integral here, is just the mean value of U. So And this integral, yeah, as we know, is equal 1. This part here is equal 1. So this is equal 1, and this value here, this part here is just the mean value of u. Okay? So the end, we will end up with the solution. A, but anyway, solution I will try A plus B mean value of u. This is our, oh sorry, okay, but this is our solution. Just please take a screenshot. We're continuing with the second part, with the variance of Q. Just gonna give you a couple of seconds. Take a screenshot, and then we will continue. If you have any question, just in the chat, or you can activate your microphone and interact with me if you have any question related to this topic. All right. Second part, this first exercise is that we have to back here. Have to prove that this identity variant of Q is equal B squared times variant of U. All right, okay. The variant of Q given by the following definition. Q function minus the mean value of Q squared U. Okay. We know from this part that we know this value here, which is this one. Yeah. So let's replace this value here in this second slide. And the value for Q2, because this part here is just this one. Yeah. Okay, let's solve this integral. This is what we obtain as a slide. Okay, value. Value. U. And then they say that A and B are constant, so end out with the following expression. And of course, we know that this part, sorry, this part here, the variance times of u. Of u. All right. Then should calculate the standard deviation of q, but we know that the standard deviation, you have to square this variant of q. So the deviation of q square according to the definition, yeah? Q. Let's continue in the following slide. Just take a screenshot to continue. Okay, I'm just gonna give you a couple of seconds. But this is quite easy because, yeah, if this is the variant of q, this one here, we have just to replace this value here. Okay? So f is just this one here, variant of u. Okay? But here again, we have this root of square variant u. And yes, this part here is the standard deviation of u. So, yeah, this is a standard deviation. Oh, okay. That's it. Okay, it's easy, I think so. And the last part here, okay, just take a screenshot. I will continue with the next slide. Please. The last part here is this part here. So, the variant of u is given by, yeah, in the integral definition, u minus the mean value or u du. Okay. But we know the value of this. Let's develop this square here. Infinity. Use the square. U. Mean value of u. Oops. U. Mean value. U. Square. If u is du. We just have to solve this integral here. Let's do it. if you will invalid square, yeah, here what we have is that this is just the mean value here, the square, and twice, yeah, value again, square, times mean value here, because this interval is just one, yeah, this does the mean value is just a constant, so we get off this mean value to square here, and the interval is just equal 1. I'm solving this. We have this one here. So just the value, mean value to square minus this mean value here. Okay. Now, this is just the variance of here. Of here. Okay, that was the last part of this first exercise. Any comments or questions? I don't see anything in the chat. Okay, thanks, Fahad. Okay, so we have this second part here. Yeah, we have this PDF. That take this value here with this interval between A and B. Oh, actually, this should be U. Okay, whatever. It's a variable. And we should show that the mean value is equal to this one, and the variance of this U, the variance of U is just this value here. Okay. First of all, yeah, what we know is that the meaning of U, using the integral definition, is given by this is very well known. EU. Yeah? With FU being the uniform distribution in the interval A and B, we have the following expression. Minus A this program is okay. Only you have to solve this integral for the first part. Yeah, let's do it. A, yeah. B here. Display here. Trouble with this display here, okay. this is just a square here. Which is the expression that we have in the exercise. So, okay, easy. Please just take a screenshot to continue with the second part. The variance. Okay, questions, comments? No? See anything here in the chat? All right, assuming that you have taken the screenshot, let's continue. In this second part, in general, the variance of U is given by U to the integral form, which is minus infinity plus infinity, U minus the mean value, everything to square, U, EU. And we just have to solve this integral. And we already know the value, this mean value. Yeah? We use this mean value here. Should replace that mean value here and the value for the function or the interval between A and B. So let's do it. Yeah. Minus the value of the mean value. The value of the function in this interval. Yeah. Minus EU. And now what we have to do is just solve this integral that for you is very easy. Let's do this, okay? Integral between this interval, because they are constant between A and B. What happened with this player? Some problem with this. Okay. Pencil is not that good. Let's continue. Okay. That will be what we have inside here. Because this is just a square. And what we have here is just U square at the first, but twice this guy here. Plus, second guy here. This is U. Solving this part. All constants. Here. U. We continue with next slide. Don't have enough space here, so just please take a screenshot to continue. This is just very easy. I'm just going to solve the integral. And the result is the result that we can find this PDF. But I will continue just developing, describing this integral, and that's it. Okay. Okay. Let's continue. Integral. Second. Here is the variance view. Space here. A. Solid. And then here B, Q. Alright, this is just a Q here. And we have A, E minus A, A. We don't have space here. I'm going to squish as. Let's continue. Okay. This denominator, we put this one, and this one, they disappear. So then what we have is just this guy here. Yeah, seems okay. Yeah, it's just the same with this one here. So this summation here. Let's continue with this guy here. This is just a cubic formula here. What we have is A square VA plus A2 parentheses 4 where I just going. Okay. Continue with the integral. Please just take a screenshot to continue in the next slide. And just solving the integral. So okay. Last one, what we have is the variance view. Square minus 4. Expanding this term here. We have C. Okay, yeah. Skip this for the moment because this is just a square. So A times AB square here. With this plus AB, okay. This. And solving this 4 here. 12 A squared AB B squared 4 here. Continuing, yeah, just this part with this part here. Wait a second. Minus 6AB minus 4. Okay, plus 12 A squared B squared 4. And solving the B squared. AB and 12 A squared. A this point. Yeah, there we are. This part is just okay. Square minus, yeah, ABC. The variance of U. Yeah. Any comment or questions or any doubt that you have related to the lecture or related to these exercises, just please let me know in the chat or use your microphone, please. Okay. Don't see anything in the chat. Okay, no questions. Any other comment? Okay, Fahad, Karen, thank you. Okay, guys, this is not the case. Thanks for your time. See you next week. Yeah? Yeah, Muhammad Absi. Thank you. See you next week. Bye. I just please take a screenshot if you don't.